Welcome back everyone. In today's lecture, we are going to discuss what happens when a dynamic system undergoes free vibration. So, in the previous lectures, we have seen that when a structure is subject to dynamic load, then we learned how to set up the equation of motion. Now, in subsequent classes, including today, we are going to looking up or we are going to be discussing some special cases that can be analytically solved. Okay, and we are going to start with the simplest case of dynamic loading, which would be free vibration, in which case a structure is basically assigned some initial condition like displacement and velocity, and it is allowed to let vibrate without any external force acting on it. Okay, all right, so let us get started. Till the lectures that we have done so far, we saw that how to set up basically the equation of motion of a system under action of an external force. Okay, and we derived that the equation of motion can be written as Fi plus Ft plus Fs, and that should be equal to the applied force. And for linear system, we saw that we could write it as mu double dot, then cu dot, and then ku should be equal to p of t. Okay, so in up to the last chapter, our focus was to derive or to finally come up with an equation of motion which is of this form for a different type of system. Okay, so we had different system under the action of a external load, and we saw that how to derive this equation of motion. Now what we are going to do, we are going to study special cases of this equation of motion for different type of vibration. Okay, now depending upon what is the external load and what my system comprise of, we are going to deal each of we are going to discuss about each of these systems one by one, and then see what are the application of those type of systems, and then how do we actually or like how do we physically interpret those systems. Okay, so if you look at these equation of this equation of motion, we basically have three components. Okay, now depending on whether we have a value of damping, okay, zero or non-zero, and what is our force of excitation. Okay, based on these two important parameters, we are going to discuss different properties of a dynamic system. Okay, so for example, let me characterize what happens for each of these cases. So in general, we saw that we had equation of motion. Okay, now we draw something like this, then when damping is zero, okay, so when damping is zero, we had free, or let us say, let us start with that when the applied force is equal to zero, so Pt is equal to zero in this case, then we will have what is something called as free vibration. Okay, so this is free vibration, and under this free vibration, depending upon whether my system has a zero or non-zero value of damping, okay, we can either have undamped free vibration or damped free vibration. Okay, so again we are going to characterize between undamped free vibration or damped free vibration. So remember that this was for Pt equal to applied force equal to 0, this is C equal to 0, okay, and this is C not equal to 0. Okay, so this is the one categorization, one tree branch. In the other part, we have what we are going to discuss, not a zero value of applied force but a non-zero value, in that case, we are going to discuss some specific cases. For example, what we are going to start with, if we have non-zero value of non-zero value of the applied force, we'll have forced vibration. Okay, and depending upon the nature of forcing function, okay, we going to study a few specific cases and then few generalized cases. So we can have, like, harmonic motion. So when I say harmonic, I mean something of something similar to something combination of sine and cos. Okay, and then we could have a non-harmonic motion. Okay, so we are going to say, let us say here, non-harmonic motions. So we could have, let us say, so this one would be like, something like sine, cos, etc. Okay, non-harmonic could be like, something like step functions, or like, pulse excitations or things like that. And then we'll have random excitation. Okay, and in random excitation we have, let us say, earthquake excitation or seismic excitation. Okay, so depending upon what is the nature of the forcing function, we are going to study all these topics. And then of course, like, in each of these topics, we are again going to study, damped and undamped. Okay, so again we'll have damped and undamped, and we are also going to discuss that how we are actually going to obtain the response of those systems. For example, if you have harmonic excitation, like, it is feasible to obtain an analytical solution or a mathematical solution which is a closed form solution. For non-harmonic cases, if for very few specific cases, we would be able to obtain analytical solutions. Okay, for random excitation, it is not possible. The like because the excitation cannot be represented as a simple, like, combination of functions that are amenable for mathematical solution. So in that case, we are going to study how do we obtain solution using numerical methods. Okay, so we are going to study that as well. Okay, now today what we are going to do, okay, we are going to focus on this free vibration. Okay, what we are going to focus on this case today as free vibration. Okay, now, as I said, what do you mean by free vibration? Okay, free vibration happens when you basically imparts an initial velocity or displacement to a system and let it vibrate without any action of external load. Okay, so basically in short, okay, basically in short, what we will have as Pt equal to 0. All right, so this is the condition for free vibration. Without any action of external load, we let it vibrate freely. Okay, and we will see that for this type of system, we could have either undamped free vibration, okay, or we could have damped vibration, and we are going to study both of these today. Okay, now the question becomes that, how do we impart or initiate free vibration? Okay, so one of the ways to do that, because we just said that there is no external force, the question, like, how does the motion start? So we, to start a free vibration, we impart either initial displacement to the system. Okay, so it would be either initial displacement of the system or initial velocity. Okay, so initial displacement means u0, or initial velocity would mean u dot 0. And, like, you can see there are a lot of example for this type of system. For example, if you take a pendulum and then you lift it, or if you provide initial angular displacement of, let us say, theta naught, all right, and let it vibrate, okay, then it would go under the action of, it would basically undergo free vibration. Okay, so that is one example. There are other examples as well. For example, initial velocity would be something, I mean, you take a hammer and then you hit something, let us say an elastic system with that hammer. Okay, and then that would be basically imparting initial velocity, because in that case the hammer imparts a lot of force in a very small amount of time, so it does not have time to react, so it won't have initial displacement as such, but because of the high, large force in a short duration of time, it would acquire initial velocity. And we're going to discuss that, that is called impulse, and how do we impart that. Okay, so these are the two conditions through which we can initiate free vibration in a system. All right. Now, these type of system, or this type of motion, free vibration, as I said, because it is without action of any external load. Okay, this type of system can be utilized, or this kind of motion can be utilized to obtain basically important parameters of a oscillatory motion. Okay, for example, so let me just write it here: to obtain important parameters and two important parameters. Okay, and we can do that experimentally. So two important parameters are basically, what is the, and we are going to define that, what is the natural frequency, okay, and what is the damping ratio. Okay, so these two parameters can be obtained using the free vibration of a system. Okay, uh, so it is like, it becomes very imperative that we obtain analytical solution for the free vibration of a system. Okay, so the first thing that we are going to do in this chapter would be undamped free vibration, and then we are going to go to and discuss the damped free vibration. Okay, so first thing we are going to discuss is undamped free vibration. So remember, this is a free vibration and this is undamped. So free vibration means Pt is equal to 0. Undamped means C is equal to 0. Okay. So basically our equation of motion becomes what? If you substitute these two equation of motion, I basically get this. Okay. With, of course, we need, as I said, we need to have an initial condition. Otherwise, if you solve this differential equation without an initial condition, you would get a trivial solution. Okay, so the initial condition, a non-zero, need to be a non-zero initial condition. Either what should, no, sorry, what should be the values of u of 0 and u dot of 0, and one of them must be non-zero to initiate the free vibration. Okay, so these two conditions need to be utilized. All right, so what we are going to do, first we are going to solve this system and obtain the analytical solution for u of t. Okay, and then we are going to get into the physical interpretation of the response for the free vibration. So solution to a second order linear homogeneous differential equation. Remember that we now don't have any term on the right hand side of this equality. So we discussed that the how to get the solution of a homogeneous differential equation. Basically, let me write my general solution u of t as e to the power lambda t, and then we are going to substitute it back to the original equation, so that I get, after substitution, plus a, and that should be equal to 0. Okay, now e to the power lambda t term would never be 0, it won't give me any feasible solution. So the only thing that can be 0 is what I have in the brackets here, and that gives me the value of the lambda. So there would be two roots of this equation. This is the quadratic equation. It would be plus minus under root minus k by m, okay, which I can write as under root k by m, where I represent under root of minus 1 as the complex number I, okay, and this is nothing but let me just fix the view, yeah, so that I can write this as I omega n, and we are going to discuss the significance of this omega n and this parameter. So we are going to do that, but let us first substitute our roots to the original equation, which is u of t. Because it has now two roots, I am going to write my solution as a linear combination of e to the power lambda 1 2, which represents the solution with respect to the first root, and then e to the power lambda 2, which is corresponding to the second root. Okay, so I will get here as, and then b e to the power I omega n t. Now if you remember from your complex numbers theory, what did you have? If you have e to the power ix, you could write it as cos x plus I sin x, remember, and then e to the power ix minus ix can be written as cos x and minus sin x. So if you make that substitution in this equation here and then again rearrange the term, okay, you will get something like a plus b cos omega nt plus, okay, let me just fix it here. I will get it as cos omega nt plus I a minus b sin nt, and again these two parameters can be represented as another constant, the values of which need to be determined to obtain a specific solution this equation. So I'm going to represent as another constant omega n and then d sin omega nt. All right, so I have obtained the solution to this second order homogeneous equation, linear homogeneous equation here. Now I have two unknown constant, and that we are going to determine using the values of the using the provided initial conditions. Okay, so let us substitute those values. Before that, I need to differentiate it once to obtain the expression for u dot t. So if I do that, I will have as minus c omega n, sorry, this should be sin omega n t here plus t omega n cos omega n t. All right, so let us substitute these values. So u0 is equal to c, and remember at t equal to 0, cos omega n t is basically, it would be 1 plus 0, because sine of omega n t at t equal to 0 would be 0. So I have obtained my value of c as u of 0. Okay, now u dot 0 would be equal to, this term again would be equal to 0 plus I will have d omega n, and then the value of cos omega t would be 1. Okay, so that gives me the value of t as u dot 0. Okay, if I substitute this to the equation that I had, the expression that I had for ut, I would get it as u of t is equal to u of 0 cos omega nt plus u dot of 0 sin omega nt. All right, so this is the solution of free vibration for the initial condition u of 0 and u dot of 0. And of course, depending upon whatever the values of u0 or u dot 0 you have, you can obtain the specific or like a numerical value of u of t. Okay, so just means just let me write it. This is as free undamped vibration. Okay, so as you can see, I have the expression for u of t, and let us just try to plot this function. Okay, and see how does it look like. So I have a cos function and then I have a sine function. Okay, so if you plot it, if you plot these expression, okay, so what I have here is, all right, and then this is u of t, and okay, so I can write it as, so if you plot it here, it would look like something like this. Okay, uh, so what do I basically see here? My resultant function is actually, or the expression for ut is actually a harmonic function and also a periodic function which repeats itself. Okay, so it repeats after a specific time. Okay, now if you look at this graph here, I know that whatever the initial displacement at time t equal to 0 was u of 0. Okay, and the slope, initial slope of this ut is basically the velocity, which I'm going to write it as a u dot of 0. Okay, now in this case, if you look at this, or let me just write it like this, take it from here. So it has some kind of periodicity, this function here. Okay, and this periodicity is actually, if you saw this function, if you see the function here, it actually repeats itself after a, or after 2 pi by omega n seconds. Okay, and that you can prove by substituting or finding out the value of ut at time equal to t, as well as t plus 2 pi by omega nt. Okay, you can find that out from this, and you can prove that the values are still the same. Okay, now this quantity here, 2 pi by omega n, and that all the time after which it repeats itself is called the natural time period of the system. Okay, so this is called natural time period of the system. Okay, and remember that the value of omega n that we have obtained is under root k by n. So now the value of Tn would become, using this relationship here, 2 pi under root m by k. Okay, so as I said, Tn is called the natural time period of the system. Okay, and omega n is actually called the natural circular frequency of vibration. Okay, so it is called natural circular frequency of vibration. Okay, and as you can see from this relationship, omega n is actually related to Tn using this relationship here. Okay, and the unit of omega n is actually radian per second. Okay, and then there is another parameter which is called the natural cyclic frequency of vibration. Okay, and we represent it using f, and it is called natural cyclic frequency of vibration. Okay, and the unit of this f is actually, first let me just write down the relationship between f and omega n. So they are related, as you can see. F is basically, first write me in terms of the time period, is 1 by t. Okay, so this is the cyclic frequency of vibration. Okay, and it is also related to omega n using this relationship here. And the unit of f is actually cycles. Many places you will see it is written as cycles per second, or in short CPS, but more commonly you will see that hertz as being used as the unit of the natural cyclic frequency of vibration. Okay, now we are using the word natural quite a lot. So you just have to keep in mind the significance of the word natural is basically that this is the natural means that it is without any action of external load, and it is for an undamped system. So these natural properties are, so maybe I'll just write it here. Natural properties are defined for undamped system. Okay, without action of external load. Okay, now it is very important to understand, the physical significance of these parameters, and what are the typical values that you would see for these parameters. Okay, now time period, as I said, it is basically the time required to complete a single cycle of motion. Okay, now if I have this graph here, and if I had to represent it, let us say for a system, the spring mass system that we have discussed. Okay, right. So let me say this is A, this is B, and I can take that for, like, for any section of this vibration cycle that I see here. Okay, it would be C, D, and E. Okay, so the motion is always considered about the equilibrium position. Okay, and for many cases, like, equilibrium position is also the initial position or the undeformed position, which is fine. For example, when we considered the motion of a hanging the spring mass system hanging from in the vertical direction. For that we said that let us consider the motion from this position. So the initial position was equilibrium. Okay, and then what we do, either we impart an initial displacement or initial velocity. Okay, or a combination of both. Okay, so this starts from, let us say, a value of, if I'm measuring you from the equilibrium, okay, starts from a value of q equal to whatever the initial rate is provided. So that would be, let us say, case A here. Okay, then what happens, as u is increasing, it attains a, or goes to a maximum, let's say in this case somewhere around here. Okay, and this is the maximum displacement of the system due to initial velocity and displacement. Okay, and this is the position B that is shown here. So this is position A, this is position B. Okay, so it will go to this maximum position, and then it will start coming back to the initial equilibrium position. Okay, all right, so this would be again C here. Okay, and then it will go with the, so when it goes to a maximum value of the displacement right here. Okay, u would be maximum, but the velocity would be 0. Okay, and that you can see from this cycle here. As it goes from A to B, you can see the displacement is maximum. However, this curve is actually flat here, which means that the slope of the this expression is 0. The slope is actually the velocity of this spring mass system. So the velocity is 0. All right, and then it starts coming back to its original position. Okay, and then it passes to its equilibrium position, at which its displacement again becomes 0. However, it passes at the maximum velocity. So at this point is when is your velocity is maximum. Okay, and that velocity carries this system in the opposite direction, so the negative u direction, as you can see here. Okay, so I'm going to represent that, let me say here. So this is the state D, which correspond to the negative maximum. Okay, and then again after it attains this negative maximum, it start coming back to its equilibrium position, at which it completes a cycle of motion. And this this actually keeps on repeating. Okay, so this is the basic, like the breakdown of a free vibration of an undamped system. Okay, now let us come back to these three parameters that we talked about: the time period, the circular frequency, and then the cyclic frequency. Okay, and as I said, that units would be second, here it would be radian per second, and here it would be hertz. Okay, so now what do you think if I have two systems, a system A and a system B? Okay, now system A, if I'm saying to you that a system A has very high frequency, okay, very high frequency. Okay, of course, this would be in comparison with system B here. What are the things you can deduce from this information that has been provided to you? Okay, if it has a system has a high frequency compared to system B, there could be multiple possibilities. One could be, or like let us just list down those possibilities. If the frequency is high, remember that how is the frequency, how is the time period connected to the frequencies? Is time period is either 2 pi by omega n, or it is also 1 by f. So it is inversely proportional to the frequency. So that means the time period would be small tn, okay, large tn. Okay, what other things you can deduce? Remember that my omega n is nothing but k by m. So if the frequency is higher, that means it could be a stiff system, okay, compared to a flexible system. And I mean, this makes sense, isn't it? If you consider a flexible system, can you physically imagine that a flexible system would take more time to come back to its, or like finish a cycle of motion compared to a stiff system? Okay, a stiff system, if you give initial displacement, it vibrates at a very high frequency. Okay, high frequency means that there are a lot of, or there are like higher number of cycles in a single second of motion, which is basically consistent with its definition here, 1 by f. Okay, other possibility for the given scenario would be, instead of saying stiff system, flexible system, for a given same stiffness, this could also be possible if the mass is small here. Okay, so let us write down a small mass, and then here it is large mass. Okay, so these are the few of the possibilities that might result in high frequency system, a system A with a high frequency compared to a system with B with low frequency. Okay, so this you have to keep in mind. If a system is stiff, that means that it would have high frequency. Okay, If a system has very large mass, that means that it would have low frequency. Okay, or I can also say that if a system has very large mass, that means, or a flexible system, then it would have large time period of oscillation compared to a system with a small mass and a stiff system. All right. Okay, once that is there, let me come back to our expression for u of t again, which we had obtained as u of 0 cos omega nt plus u dot 0 omega n sine omega of nt. And remember that we said that omega nt I can write this as 2 by t. So I can also write this expression as okay, and then I can write this as similarly 2 pi by t by tn. Okay, now remember that we know from this graph, okay, what is u0, what is u dot 0. We have also find out what is the time period of vibration or the oscillation. Okay, there is one more thing that is remaining to find out, remaining to be found out, and that is the amplitude of the oscillation here. Okay, let us represent this using u naught. Okay, so amplitude would be basically whatever the maximum value of this expression that I have here. Okay, so I need to find out maximum value of ut. Okay, let us see how do we get that. If you consider any function of type a cos, let's say a cos theta plus b sine theta. If you remember your trigonometric identities, what I can do here, let me multiply and put this case here. I will multiply and divide by this. Okay. So under square root of a square plus b square. Okay, and if you look at this carefully, if I consider tan alpha equal to b by a, then this expression is nothing but sine of an alpha, and this expression is nothing but cos of alpha. Okay, where tan alpha, as I said, is b by a. So I can write this further as under root a square plus b square, and this would become cos theta into cos alpha plus sine theta into sine alpha. And from your trigonometric identities, I can write this as cos of theta minus alpha. Okay, and that we can, like, substitute it back here. So in this case, remember my a is u of 0, b is u dot of 0. So I can write this whole expression as u of 0 and cos of theta minus, let us say I represent this instead of alpha, I will say this as phi. Okay, now I know that maximum value of cos function is actually plus 1, so that the maximum value of ut would be, let me write it as u naught, with this. Okay, so the free vibration with initial displacement and velocity happens around its static equilibrium position with an amplitude which is represented by this here. Okay, all right, once that is clear, okay, let us see how do we find out the important dynamic properties of the system. Okay, till now we were deriving our equation of motion as mu double dot plus cu dot plus ku equal to p of t. We said that for a free vibration, this equal to 0. For an undamped free vibration, this equal to 0. Okay. So a simple problem on this would be a system, an undamped system would be given to you. Okay. And you could be asked to find out what is the value of omega n, which you have to find as k by m. Remember that there are multiple ways to obtain the equation of motion in terms of different degrees of freedom as well. Okay. However, whatever you do, the omega n should be same, because remember omega n depends on the stiffness and the mass of the system. It does not depend on the applied load. So it is a property of a system. Okay, it does not depend on the applied load, so that you have to keep in mind. Okay, so once I write this expression omega n equal to under root k by n, you can obtain the equation of motion differently with different coefficients. Okay, point is, what I'm trying to make here is, whatever the way you obtain your equation of motion, your omega n should be in the simplest form coefficient of the stiffness term or stiffness force. Okay, so basically here, okay, divided by m, which would be the again coefficient of, instead of saying stiffness force, let me just write it as coefficient of the displacement. Okay. The second term I can write it as coefficients of the acceleration. Alright, so using this I should be able to obtain my omega n, which is of, again as I said, it's in radian per second. Okay, and then I can find out the time period of the system as well as the frequency of the system. Okay, all right, I hope up to this point it is clear to you. Okay, now what we are going to do, we are going to do an example. Okay, and this is not a problem for a book. What we are going to do, we are going to take typical properties of the values of a system, of a building, let us say, with a column and beam, and then see what is the value of the time period that we get. Okay, so let us say a typical single story building is, what do you think is the typical size of a room would be? Okay, it might be, let us say, 10 feet by 10 feet. Of course, if you live in Mumbai, then it might even be smaller, isn't it? Okay, anyway, so let us say I have this and I want to find out the time period of the lateral motion. Okay, there was a problem, remember, in which we had considered torsional motion, but right now we want to consider only the lateral time period of the system. Okay, so let us say, I mean, there are 4 columns. A typical column could be 300 mm by 300 mm, and there are 4 of those, remember. E of concrete, let us say it is 25 MPa concrete. Okay, so let us say it is 25 MPa concrete column. Remember that E is nothing but 5000 times under root FCK. Okay, so I would get as E as 2500. Okay, 2500 MPa. Okay, and if I consider these not to be actually, let me just again write it, or let us just say this is the fixed connection, although in reality it is not like always fixed. There, many times it would be plain, because to provide fixity we need to do additional detailing and provide rigid support to the ground. Okay, but anyway, just for the sake of this calculation, let us assume it's a fixed connection. Okay, so remember that what was our stiffness in that case was 12 EI by L cube. Okay, and a typical story height you can assume as, let us say, 3.5 meter. Okay, so if I substitute it here, I will get as 12 times E, which is 2500 MPa. Okay, and this I can write in 1 ampere. Remember, 1 MPa is nothing but 10 to the power 6 Newton per meter square. And what would be I of a section? Okay, so if I have a section like this BD, remember, if it is bending about this axis, then it would be, I would be BD cube by 12. In this case, both are same, the square cross section, so I can, it would be just 0.3 to the power 4 divided by 12, that is my EI, and the length is 3.5 into the power cube. Okay, and this need to be found out, so you can calculate this value. Okay, let us see what do we get when we calculate that. Okay, so I get it as 47230P. Okay, and that would be, let us say, Newton per meter. Now in terms of mass, what I could do, I could lump all the masses here. Okay, so half of the mass of all this, and remember this is for one column, sorry. So what I need to do is use 4 times, which let us say I'll do in the final calculation. Let us first talk about the mass. Mass, you can lump it at the roof level by assuming that half of the mass of these columns are lumped to the roof slab here. Okay, and then the dead weight of the roof slab, you can add it to that. Okay, and then you can also add the live load. Okay, and all those would contribute to the total mass of this system. Okay, so for the mass of the system, let us say I have 4 column, and I would assume that half of this is actually lumped. Okay, now remember that cross section area is 0.3 by 0.3, and then I would have to multiply this with 2400, which I'm assuming as the density of the concrete. Okay, this is for the column. For the slab, let me assume, like, typical slab of 250 mm. Okay, so in that case the total would be, remember that the slab dimensions, I can assume this has to be 4 meter by 4 meter. Okay, so it would be 0.25 thickness of slab times 4 times 4, and then again 2400. So this is basically the dead weight. Okay, but in reality there are other type of things as well. For example, floor finishing is there. There might be, like, other things that are installed on top of it. Because I don't have information regarding that, I'm going to neglect that. However, what I'm going to do, I'm going to assume a live load to this slab here. Okay, which I would assume as a live load acting as 3 Newton per meter square. Okay, which is very typical, so I will write it as 3 Newton per meter square times the area, which I have here is, okay. And remember that I need to convert this into mass unit system here. Okay, so this is Newton, so to convert it to kg, I will multiply this with 9.8. Okay, so let us see how much I get. 4. Okay, so I'm getting as kgs. Okay, so let us say if I use this, what do I get as time period? P, so the mass, and then I have 4 of these column here. Okay, so I get it approximately as 0.5 second. And as you, like, do more and more problems and calculate the time period, you would see that 0.5 second is very typical of, like, low to medium rise building. As the height of the building increases, the time period would actually increase. But using these typical values, we have obtained the time period to be approximately 0.5 second. Okay, so depending upon what kind of structure it is, I will give you some typical values of the time period of different type of structure. Okay, so buildings, depending upon whether it is a low and low rise building or a high rise building, it could be between, let us say, 0.4 to 1.5 second actually for a high rise building. If it's a very stiff structure like nuclear power plant or something like that, okay, then it's a very stiff structure, so the time period would be very small. It is around 0.2 seconds. Okay, you get typical values between 0.2 to 0.3 second. Or you could have very flexible structure like a suspension bridge. Okay, and which could have, depending upon which direction you are considering, time period even 7 to 8 second in one direction, or 3 to 4 seconds. So depending upon the direction, you could have different time periods which are of typical values, varying around 6-7 second or 3-4 seconds. So it's a good practice to keep these values in mind, to reflect what are the typical values of different type of systems for their time period and frequencies, just to get a feel of these numbers and these parameters. All right, so with this I would like to conclude the lecture today. Thank you very